All right, we're going to take a look at the occipital lobe here. Let's see what we got. Let's start off with where it's located. It's located in the back of your brain, so it's right behind your parietal lobe and just behind your temporal lobe. So it's located in the very back of your head back here. All right? So it's basically responsible for everything that we see and we perceive. So our eyes as receptors pick up light. That light is then channeled back through our optic nerve, through our brain, to the occipital lobe. And the occipital lobe plays a part in helping us actually perceive what it is that our receptors, our eyeballs, are actually picking up. All right, so basically what you should understand is if you have a blow to your occipital lobe, it could cause a person to black out. So you often think if you punch somebody in the face, that might make it so they can't see. You might actually hurt your hand and you might hurt that person's eyeballs, but they might not black out. But if you hit somebody in the back of the head, a blow to the back of the head is probably going to cause somebody to lose their vision. That's why in boxing, people aren't allowed to actually punch people in the back of the head because they'll not be able to see. They won't be able to perceive what they're looking at. Okay, so right at the very tip of the occipital lobe, at the end part there, is what's called the primary visual cortex. That's the part that receives electrical signals from the receptors in the eye. So that's the area that is really the primary part where our vision is processed and helps us to perceive the things that we see. Okay, so here's a quick little diagram. You can see on the right-hand side of here, we got basically an eyeball. We have a lens here. And that lens is then, of course, connected to the rest of the eye through to the optic nerve. And that optic nerve is then what channels that signal to the back of the occipital lobe. So if I look at this little diagram at the bottom here, you can see the eye picks up light, perceives that information. It's sent through the optic nerve, which then transmits it eventually back to the primary visual cortex on the occipital lobe. So it's kind of counterintuitive, but the idea here is that our vision is processed on the back of our head, not necessarily in our eyeballs, which are really just receptors for picking up the light. Okay, let's take a look then at that visual pathway. And this diagram on the right does a pretty good job of showing this. Basically, nerve impulses are going to flow from the back of the eye towards the primary visual cortex. And in this diagram, you can see that things that you see on your right field of vision are actually going to be sent to your left hemisphere, to the left side of your brain. Okay, so they'll end up in the left hemisphere, the left primary visual cortex of your occipital lobe. And then things that you see on the left-hand side will actually go to the right side of your brain. So it's the opposite. Everything I see on this side goes to my left brain, and everything I see over on this side goes to my right. So it's the opposite. The brain switches the vision around. And it's not just what you see on the left and right, it's per eyeball. So if you notice on the diagram, you can see in both sections right here, there's a left and right field of vision that goes to the left hemisphere or the right hemisphere per eyeball. So essentially, you could lose an eye and still have your two hemispheres be able to process the vision that you see, even if you were a cyclops with just one eye. You'd have to move your eye around a lot, but it would actually work. Okay, so here's an example of what happens. So for primary visual cortex, let's say we'll look at the left-hand side. We've got this guy who's dressed in blue. Looks like he's playing a guitar. This is what my eye sees. I see these shapes. I see these colors. They're sort of just random patterns and just light that's picked up by the receptors and then sent back to the primary visual cortex. And what happens is the occipital lobe, right, the primary visual cortex, takes that in the visual association area, and it has to recombine those to make it into, in this case, what appears to be a guy dressed in blue playing a guitar. So it takes those shapes and colors, right, I'll go back a second, takes that disparate shapes and colors, and it turns it into this. All right, so I can actually recognize it as a thing or a person or some kind of an event. Now, if somebody has visual agnosia, they also see that same disparate set of colors and shapes. The problem is in their visual, in the back of their brain, in their visual processing center, they cannot take that and turn it into, in this case, what it is, a guy playing a guitar. That's what they see. They're not able to sort of reconnect and put the pieces together. So visual agnosia is where somebody has a problem processing what it is that their vision. And you can see where that might be a problem for somebody in perceiving the world in which they live. They don't see the world literally the way that other people see it. Okay, so let's throw a mental imagery task at you. I'll throw the first one here. We'll start off with a typical round cake. I want you to kind of envision in your mind, close your eyes for a second, and think about what a round cake looks like. It should look like this, like a round cake. All right, now, let's say a friend of yours gives you a big knife and challenges you to cut the cake into 8 pieces, but you only get to do it with 3 cuts. Okay? So you got to cut that round cake into 8 pieces, but you only get to do it in 3 cuts. What I want you to think about is how would you go about solving that puzzle? Think about it. Take a minute for a second. You can pause this screencast and think about your answer. If you want to write it down, go ahead and write it down. But think about how you would do it. What would be the process by which you would figure that out? 8 pieces, but you only get 3 cuts. All right, ready for the answer? Here comes the answer. All right, you're going to take 2 cuts, and you're going to cut the cake into 4 equal pieces. 1, 2. That will get you 4 quarters, okay? And then you're going to slice through the center of the cake the opposite direction, that 3rd cut, and you'll cut the 4 pieces into half horizontally. That will be perpendicular to the first 2 cuts. That should get you 4 sections from each layer, basically, which will get you 8 pieces of equally distributed cake, but you're only doing it with 3 cuts. Now, that's the answer. Not everybody comes up with that answer because it's difficult to do. Because in order to come up with that answer, you have to be able to perceive this cake in your head and do more than just see the cake. You have to be able to do things with the cake in your mind's eye. So, here's what happens. You've got what's basically going on. It's mental rotation and mental imagery skills to help you visualize the potential to answer for this puzzle. So for instance, in the back of my occipital lobe is where this is going to be processed. And you can see on these diagrams here on the right hand side, you can see that the parts of my brain that light up when thinking through this process are in the back of my head in my occipital lobe. Okay, so first, I've got a mental image of a cake that's rotated in my mind's eye. So not only do I have to be able to envision and see a cake when I close my eyes, I have to be able to rotate that cake. I have to be able to move it around in my mind to be able to solve this problem. So I'm also going to be using my occipital lobe for that visual perception. So visual perception takes place in the occipital lobe. The parietal lobe is actually going to help me to perceive that object in space. That's one of the tasks that the parietal lobe does. It sees things dimensionally and figure out its shape and its size. And then the frontal lobe is also going to be employed for executing the function. So staying focused on the task and trying to achieve the task requires I use my frontal lobe. So my occipital lobe, my parietal lobe, and my frontal lobe are all playing a role in this task. Why this is important is it helps us understand the process that lobes don't function by themselves, that the different lobes are interconnected and working together, they can solve complex mental issues like how to cut a cake into 8 slices and get everybody a piece with only 3 cuts. Okay, take a look at this task. Which piece fits into the space on the box at left? Alright, so in order to do this task, you have to try to figure it out. Is it A, B, C, D, or E that's actually going to go into that? You're looking for the particular shape that fits in. Alright, so you might be trying to think about it, but in order to really pull this task off, you have to use the same type of thinking skills. You have to be able to use mental rotation. So in this case, try mentally rotating some of those shapes in order to see if it fits. So let's take a look and see what the right answer is. Is it A, B, C, D, or E? If you picked C, then you're correct. Because again, what I have to do is I have to take C, I have to rotate it, and then as I move it over, I'll see that that actually fits in. But again, if I can't mentally rotate that shape by just looking at it, it makes this task much harder to do. Okay, now there's all kinds of visual phenomena that you can look at. Optical or visual illusions, we usually refer to them as. Now, most effects have their basis in the visual pathway. So depending on the type of optical illusion you're looking at, it may not actually be taking place in your eyes, and it may not be taking place in your occipital lobe, but also along the pathway, the visual pathway on its way to the occipital lobe. Again, it's going to depend on the type of effect that you're actually looking at. These effects don't always originate in the optic of the eye, though. Some do, but not all of them do. All right, so let's take a look at this. Here's an illusion. What I want you to do is I want you to look at that circle that's on the inside of the larger circle. I want you to understand, is it the same shape or is it different? All right, is it circle or is it not a circle? And so look at that for a second. All right, so think about your answer, and here it is. It's actually another circle. So it's a circle within a circle. But when you go back and look, it kind of looks distorted. All right? Here's another one. Now again, if you look at that long enough, it should start to move. It actually is spinning to the left, so it's spinning counterclockwise. And the more you move your eyes around, the more you'll see that taking place. Now here's another one. These ones here look like they're spreading apart if you stare at it long enough. Really kind of unusual. All right, here's another one. Again, the spinning, especially the white things in the center, are spinning counterclockwise, and some of the outer ones are spinning a little bit as well. All right, this one here, if you stare at it long enough, you'll start to notice that the squares are kind of sinking in towards the middle. Again, it's an illusion, they're not really doing that. This one here, the circles, they're all kind of focusing down to that center point as you stare at it. Okay, there is going to be a list of different optical illusions that you can go look at in Blackboard, so if you get a chance, make sure you go look at them. There's a whole bunch of them, and you should, for homework, go play with those and read the descriptions about how they all work. They're all pretty cool. And in addition to that, there's a video that I would like you to watch, the brain's ability to change. And here is the answers to some of the questions I want you to think about after you've watched this video. So the visual cortex processes the sense of touch in people who are born blind. So blind people have very sensitive fingertips. And the problem is that because they're blind, they're not using their occipital lobe. Remember, vision's processed in the occipital lobe in the back of the head. As a result of it not being used, the occipital lobe finds something else to do. In this case, it makes their fingertips very sensitive so that they can do things like read Braille. So the question in the video is, can sighted people's brains rewire themselves? And what the video shows is that basically the first thing that happens is the blindfold is worn for about 100 hours straight while studying Braille. So they take a person who's not blind and they blindfold them for 100 hours straight and they study Braille while they're doing it. And then they take a magnetic device that shocks the back of the occipital lobe momentarily, and that confuses the visual cortex. And then the visual cortex will help process that information that's now coming through their fingertips. So since it doesn't have to process vision anymore, it decides instead to focus on something else. In this case, hey, I'll help you learn Braille. Right? And then the brain simply has rewired itself in just 5 days. So in 5 days, they can take a person whose occipital lobe was processing vision, and then 5 days later, all of a sudden, they're basically doing Braille, and they're doing it quite well. Right? And then, once they remove the blindfold, the brain starts to get sight again. The eyes see the light. It's processed back in the occipital lobe. And all of a sudden, it reverts back to its normal function, which is to process vision, and their fingertips aren't as sensitive as they once were. Again, why this video that we're going to see here is really important is that it shows us the malleability of the brain, that the brain can adapt to new changes, and that if one part of the brain isn't needed to do something for one type of task, it can easily adapt to do something else if it wants to. So the brain's malleable, right? The different lobes can sometimes take on the tasks of other lobes if the brain needs to do that. That's pretty cool.